So welcome to lecture 3 of EI-207 Digital Electronics. In this lecture, we'll study about logic gates, Boolean algebra and the simplifying techniques. So to further move on, the objectives of this lecture are like we have to see logic gates, then in the logic gates we will see basic gates, derived gates, and in the derived gates there are also the universal gates. So universal gates form the part of the derived gates. Then we will see various Boolean algebra identities, and then in that with the help of those identities we will understand that how to manipulate an algebraic expression, a given Boolean algebraic expression. So how to manipulate that given Boolean algebraic expression. Later on we will see that what are the various forms to represent a Boolean expression and how to later simplify using various techniques. So in simplification we will see simplification with the help of Boolean algebra itself, then with the help of K-map, which is very well known, and then later the Quine-Maklowski method or the tabulation method. So this every method have its own advantages and disadvantages. So we will see K-maps up to 5 variables, that is we will see it for 3 variables, 4 variables and 5 variables. So we'll discuss the procedure as well as the understand the procedure with the help of examples. And we will also see the same in the SOP form, POS form, and in with and without don't care, everything. Okay. So let's start with logic gates. We'll start with logic gates. What are the logic gates? So why are these basic building blocks which are known as the gates in the digital electronics? Why first of all they are called gates? So they are called gates because they actually makes the decision. Okay, so they are with the help of this particular circuits you can make some logical decisions. So that is why they are called gates. That is, they allows or like doesn't allows the flow of information. So that is what the most important thing is. That is why they are called gates. Then there are various types of gates, and these are the gates which may have minimum one input, like as in case of NOT gate, or two inputs, or there can be multiple inputs. Okay, more than 2 inputs are also possible. Whereas this circuits, you will see that usually in this course we will see gates with single output, but there are gates with multiple outputs also. So that is also possible. Then this every gate is based on the logical operator. So this digital electronics, basically when we will study the Boolean algebra, we will study the various operators. So for each operator we will have a basic gate. So we can implement that operator with the help of the basic gates. Then later on there are derived gates in which we study universal gates and non-universal gates. So we'll study those as well. So if we talk about the basic gates, then the types of basic gates are AND, OR and NOT. So these are the various these are also the basic operators which you will see in the this Boolean identities while studying the Boolean algebra. Then there are derived gates, that is the gates which are derived with the help of basic gates. So these all derived gates can be implemented with the help of basic gates also. But any gate, okay, whether it is a derived gate or a basic gate, can be implemented with the help of universal gates also. So derived gates are categorized into two types, so universal gates and the other derived gates or the non-universal gates. So universal gates are NAND and NOR, whereas the non-universal gates are XOR and XNOR. So we'll study each one of them in detail, and then we will see that how to use them to implement the circuit, okay, any Boolean expression. So let's say in this particular slide I have like tried to include all the gates which we know so far from your basic course, from your this earlier course, whatever you know. So I have tried to include all those gates here in one slide. So if we talk about the basic gates, so these are the basic gates. So basic gates are AND, OR and NOT. So what is the basic operator which is used to specify this particular operation? So AND operation, if it is implemented on two variables or two literals, then it is A dot B. So dot is the operator. So dot is basically the AND operator. The number of variables can be 2 or more than 2. It can be 3 variable, 4 variable, okay, depending upon the choice. Any gate, all the gates, any of the gate you consider, they can be two input gates or multiple input gates also. But if you want to implement them as a NOT gate, then they will become single input gate. So this is the basic operator. Dot is the basic operator for AND operation. Now what is the symbol for this? So symbol, to specify this, rather than first moving to the symbol, let's first see the truth table. So as soon as you talk about this operator A dot B, this is sort of multiplication. Okay, A dot B, A and B. So this means if both the conditions are satisfied, then only the output will be present. So we can specify this particular thing with the help of a table which is called the truth table. So truth table is nothing but a table which specifies the relation between the input and the output. So these are the inputs, this side, and this is the output. So in this case you can see that A and B are the inputs. So A and B are the inputs and X is the output. So X is the output. Now in this truth table, what we do is we write all the possible combinations of the input, and in the output column we write that which particular combination, for which particular combination the output will be present. So particular that combination we mark as 1, whereas the combinations which will be absent is marked as 0 in the positive logic. Okay, so I am talking about the positive logic. So this is what the truth table is. So if you see that when both the inputs are available, then only the output should be there. It is analogous to a series circuit. Okay, so if both a series circuit with two switches, let's say. So if you have two this switches connected in series, then you can easily understand that AND gate is nothing but AND gate, you will get the current flow through the circuit only when both the switches are closed. So this is what it is showing by 1 1. So closing of the switches is shown by 1 1. So in this case only the output will be present, else in any other case, when one of the switch is off, the output will be absent. Okay, so this is called the AND gate. So this AND gate is basically, we understood it with the help of some analogy of two switches in series, but in digital electronics this is usually specified with a usually denoted or specified in the circuits with the help of a symbol. So that symbol is this. So this is how you make it. So sort of D. Okay, so this is what the symbol is. So here we are showing the two inputs. It can be multiple inputs, and here we are showing the output. But the output can be multiple outputs as well, because every gate you will require the output of the gate, as well as sometimes you also require the inverted output. So in some of the gates you get the inverted outputs also. So that is why I am saying that each gate may have the multiple outputs also. So this was about the AND gate. Now the second basic gate is the OR gate. The OR gate is specified with this symbol, whereas the operator for the OR gate is plus. Okay, usually we understand with the help of plus, and this is nothing but in the truth table, if you try to understand, then it is a parallel switch rather than series switch, as the case was for AND gate. For OR gate, it is the two switches are connected in parallel. So if any of these switches on, then there will be flow of the current in the circuit. So we can understand that if any of the switch is on, so positive logic, on condition is specified with 1. So if either A or B or both of them is on, both of them are on, so then the current flows through the circuit. So this is the analogous thing. So this is how you show it. Okay, so this is the symbol, operator, how to show it in the equation, how to show it in the circuit, and this is what the truth table, the basic functionality of the circuit. So whenever something is given in the future unit also, if something is given, so first of all, with the whatever you know, first of all we will try to make its truth table. So once we are able to make its truth table, then we have to implement it with the help of certain symbols, with the help of that is with the help of gates, and then later on we get its simplified function. So this is what the usual process of implementing any this logical expression as well. Then we'll talk about the NOT gate. So NOT gate is the only gate in digital electronics which have single input and single output. Okay, whereas all other gates have should have at least two outputs, should have at least two inputs. Okay, so NOT gate is a gate which is specified like this, a triangle and a bubble, okay, at the output. So this is your NOT gate. So let's say A is the input, so X will be the output, and the equation to show this particular thing, it is a complement is used. So rather, I mean, it can be denoted by a bar over the variable, or it can be denoted by this particular mark. Okay, so you put up this mark there. Okay, so this is what the complement mark. So this is what the NOT gate is, and it is specified as a function like this. And the truth table, if you write, then the truth table of the NOT gate is nothing but if you give, let's say, 0 is the input, then your output will be 1. And in the other case, when the input is 1, then the output will be 0. So it is just inverting. So if you apply if low, then output will be high. If input is high, then output will be low. So that is what the usual thing about the NOT gate. Now let's talk about the buffer, which is usually can't be placed in any of the gate, because it is like two NOT gates placed in series. Okay, so if two NOT gates are connected connected back to back, then it becomes a sort of buffer, or you can implement buffer separately as well. Okay, so buffer is nothing but a 0 will give you, if 0 is implemented, then output will also be 0. If 1 is implemented, then output will also be 1. The functionality will be X will be same as, okay, the output will be same as the input. But then the question arises that when the output is same as the input, then why do you require buffer at all? Okay, so this is like the question which we face in the interviews as well. Some of the times people ask this. So the very simple answer is, this particular circuit is required to, first of all, it have many applications, okay, in the analog circuits as well as in digital circuits. In analog circuits, if you talk about, so it should be analog buffer. In digital circuits, it is used to separate the input from the output, first of all. Okay, so there are various applications where you use this buffer to increase the fan out of the circuit. What is the fan out and fan in of this particular thing, that we will understand later on, but buffer is used there as well. Okay, now let's talk about the other gates. Now let's come to the universal gates, okay, in the category of the derived gates. So basic gates are basically 3, so you understood them. Then let's come to the derived gates. So in the derived gates, we have two categories, universal gate and the non-universal gates. So first let's discuss the universal gates. So universal gates, there are two universal gates, which are NAND and NOR. So why they are called universal gates? They are called universal gates because you can implement any of these gates. Any gate given in this table can be implemented with the help of either of this NAND gate or the NOR gate. That is why they are called universal gates, right? So to implement this functionality of the NAND gate is nothing but A dot B complement of A dot B. So it is nothing but the complement of this particular AND gate. Okay, so the complement of AND gate is called your NAND gate, and that is why this symbol also have this bubble out at the output terminal. So whenever you have a bubble at the output terminal, then it is nothing but the complement of whatever you are getting in the input. So this bubble shows the complement. Okay, so if it is coming at the output side, then the output function, whatever you are getting, will be complemented, okay, with the help of this bubble. Whereas if it is at the input, then you consider it as, later on we will see that if it is coming at the input, then we show it with the help of this particular thing. A bar, if you want to represent. So if A is the input and you want to show it with the help of bar, if you want to bar here, so you will put a bubble here. Okay, so this is what the case is. Now so NAND gate functionality is this is the symbol. And what about the truth table? So truth table is exactly complement of the NAND of the AND gate. So in the AND gate, if you are getting 1 in this particular situation when both the switches are on, in case of NAND gate we get 0 in this particular case when both the switches are on. Okay, whereas 1 we get when either of the switches off. Okay, so when either of the switches off, then the output should be 1. When both the inputs are 1, then the output should be 0. So this is what your NAND gate is. Okay, then the NOR gate. So NOR gate, if you talk about, so it is complement of OR gate. So that is why a bubble is shown here. Functionality, if you see, so it is complement again. So A plus B, so A plus B bar. Again, truth table is complement of this. So that is why they are called the derived gates, because here in this these are the unique all the gates have unique truth table, but you can get the truth table of this two particular gates with the help of these two gates. So that is why they are considered as the derived gates. But they have this particular NAND and NOR gates are have the utility that they can be used to implement any function. Okay, not only this gate but any function. Now this NAND gate we were talking. So I have told you that NAND gate symbol can be this AND gate and a bubble at the output. But the same thing can be implemented with the help of OR gate and the bubbles at the input. So this is called invert OR gate. Okay, so invert OR gate, not OR. So invert OR gate it is called also as invert OR gate. So invert OR gate, if you will see, and if you apply the De Morgan's, what is De Morgan's we will study later on, but I hope you remember it from your previous class. So if you just apply the De Morgan's here, then you will understand that it will be same as this. Okay, NAND gate, and this is shown here as well in the equation. So you see here what if the inputs are x and y, so the inputs will become, or it is A or A and B. If the inputs are A and B or x and y, whatever. So with the, if the input is, let's say, x, so after the bubble the input will become x bar, right? If here the input is y, then the output will become y bar. You can consider inputs any variable. Okay, that is not a point to be confused about. But now if you just see this OR function, so what will happen? It will be OR of this two. So the output will be x bar plus y bar, right? Now with the help of De Morgan's, if you simplify it, then you can write it that it is x dot y whole bar. Okay, so this is why. That is why I am saying that this particular function is equivalent to a NAND gate. Okay, so NAND gate can be implemented, can be shown in a circuit with the help of this bubble at the output of the AND gate or the invert OR gate. Okay, so you should remember this particular thing. Okay, now same as with the NOR gate. So if you want to show the NOR gate, then the functionality of the NOR gate is a plus b whole bar. Then a plus b whole bar, again it is complement of the OR gate. So the truth table is also the complement of the OR gate. You can check it. And if you find any mistake or any error, you can just specify that to me. I'll be happy to know the mistakes and I'll correct it later on. Okay. So the NOR gate symbol is this. Now this NOR gate can also be we can show it with the help of, we can implement it with the help of invert AND gate, okay, or not AND gate. Again the logic is same. If you see the inputs, so it will become x bar dot y bar, and the output, if you use the De Morgan's, then it will become x plus y whole bar. It is same. Okay, so if you just use this, okay, so you can write it like this. Okay. So now let's come to the XOR gate and the other derived gates. So other derived gates are XOR gate and the XNOR gate. Again, let's say XOR gate if we study. So XOR gate is denoted by the functionality. This is the functionality. So this is the operator, I should say, not the functionality. So circle and the plus inside that. So that is what the operator for the XOR gate. Okay, and if you show it with the help of the basic gates, then it becomes XOR is a bar dot b plus or a complement dot b plus a dot b complement. So this is what the functionality is, and it is also called non-equivalent gate. Okay, so it means that the output will be 1 when both the inputs are different. Okay, so you see, when the inputs, the output will be 1 only when the two inputs are different. So the one input is 0, the other input is 1. So then in that case you are getting the output. Same when the input is 1, A is 1 and B is 0, then in that case you are also getting 1. And in the other cases, when both the inputs are same or equal, then in those two cases you are getting 0. So this we have shown for 2 input gates, but it is same for, the logic will be same for any number of inputs. So if it is a 3 input gate, then if all the inputs are equal, then in those two situations you get the output as 0, whereas in the other cases you will get 1. So this is what the logic, if this is what you are getting, then you call it XOR gate. Okay, so the XOR gate operator, XOR operator is this circle, and over the circle there is a circumscribing circle. So inside the circle there is a circle. Okay, so you can, inside the circle there is a plus, Okay, so this is how the operator looks like of an XOR gate. Then XNOR gate. Okay, so XNOR gate is non-equivalent gate. So non-equivalent gate is XOR was non-equivalent gate, XNOR is equivalent gate. So equivalent gate means that the output will be 1 when both the inputs are same. Okay, so this is also called the equivalent gate. So you should remember this particular gate, and this will be used in circuits when we want to make comparators. Okay, so if we, comparators, you just when I'll talk about the comparators in the combinational circuits, I'll talk about this particular, the application of this XNOR circuit. Okay, so this is called equivalent gate, and the operator for this XNOR is a circle and a dot inside that. Okay, so circles circumscribing a dot. Okay, so encircling a dot. So a circle encircling a dot. So that is what the operator for an XNOR gate. And XNOR is nothing but the complement of XOR. So this is what is shown here. The separate operator, the individual operator for that particular XNOR is also shown here. And the functionality for XNOR is nothing but if you will do the complement of this particular thing, this function A complement dot B plus A dot B complement. So whatever you are going to get is A complement dot B complement plus A dot B. So this is what the function in terms of basic gates, if you want to implement the XNOR gate, it will look like something like this. Okay, so this is what the truth table for an XOR gate, XNOR gate. This is the symbol for XNOR gate. So in the XNOR gate, we show this bubble at the output terminal of the XOR gate. So then it becomes an XNOR gate. So this was about the basic and the derived gates. So this is what all the gates we know. This gates in the previous slide, in this particular slide, we have seen in the form of truth table. Now we will try to see the same outputs with certain gates. For certain gates, we will see the timing diagram. And why I am showing you the timing diagram, because in certain softwares implementation, if you will do, or if you have to show, the counters if you will study, then in that during the counter applications or counter design, we may have to show the we have to show the output in the timing diagram form. Okay, so that is why I am showing the timing diagram here directly, for the very simple gates also, so that you have the basic understanding that what is a timing diagram, and then later on how it can be made for the other complex circuits as well, if it is required to make, if you want to make it. Then the timing diagram is nothing but what we are showing is just the same thing. Let's say the two inputs are A and B. Okay, and this inputs are becoming 0 and 1 at various instants of this time. So let's say initially the time is the input is at 0 level, so that is what is called 0 level, that is the high level. Okay, then this is transiting, so that is transiting or the falling edge. Okay, so this is falling to 0. So this is this is where I am showing you the output 0. This is the logic 0. So this is transiting, then it is again rising. So this is, if it is rising, then it is called the rising edge. Okay, so it is transiting from 0 to 1. So this is rising edge. So when it is falling from 1 to 0, it is called falling edge. When it is rising from 0 to 1, then it is called the rising edge. Whereas these two levels are called the levels. Okay, so this is what it is. Now we are assuming here that the signals have like 0 fall time and the 0 rise time. Usually we are considering here the ideal condition, but this is not the usual cases. In the practical cases, there will be some this particular time. Okay, it will not fall instantaneously. But in the ideal course, this course particularly, we will consider the ideal waveforms. Okay. Okay. So, okay. Now let's say these are the two inputs which are becoming 0 and 1 at certain instants. So, okay, in this particular, how to read this timing diagram. So, in this particular time range, these two inputs, this A is 1, whereas B is 0. Okay, in the other from T1 to T2, in the range T0 to T1, the output A is 1, whereas B is 0. In the range T1 to T2, A is 0 and B is also 0. In the range T2 to T3, A is 0, see it is at 0 level, and B is at 1. Okay, so you can read the this timing diagram like this. Okay, this particular region, then this particular region, then this particular region. So this will give you one combination of the truth table, this will give you the second combination of the truth table, this is the third combination of the truth table. So this is how you have to see. So every row, okay, so this is, you can see here in the timing diagram like this vertically, whereas in the truth table you see it horizontally, okay. So these are the various things. Then for, let's suppose you are implementing a AND gate. So if these two are the inputs of the this particular AND gate, so what will be the output? How you will show it in the on the timing diagram? So to show it on the timing diagram, what we do? We multiply these two waveforms together. So you see, if this is 1 and this is 0, and if you multiply them, what will be your output? It should be 0, right? So this is how you are showing it. So it is 0, right? In this case, in either of the case, because you see, what we will do is, like, we'll try to exhaust all the conditions of all the possible combinations of the truth table. So while drawing this timing diagram, we should understand that all the possible combinations should be included here, okay. If we miss out, then we may not be able to verify the things. So while drawing this timing diagram, you should be very careful that you have considered all the possible combinations, you have drawn all the possible combinations of the truth table or not, right? Okay, so if we see the AND gate output, then it will look like this. So in up till here, if you will see, either A or B is 0, so that is why you are getting the output as 0. In this particular region only, between T3 to T4, both the inputs are 1, so that is why you are getting the 1 here, okay. So this is how you draw the point here is just to show that how to draw the timing diagram of any functionality. So we have chosen 3 functions: AND gate, OR gate and complement. So let's say if you have to draw this, then how to draw it. So we have seen already how to draw the timing diagram for an AND gate. Let's see the timing diagram for the OR gate. So in this particular region, if from your previous slide, if you remember, then you know that the output will be 1 when either of the input is 1, and the output will be 0 when both the inputs are 0, okay. So you see here in this range T1 to T2, both the inputs A and B are 0, so that is why your output is 0 in this range for an OR gate. Whereas in any other case, in any other region, if you see, then the output is 1, okay. Then complement. So complement of what it is? This is, I have already told you that this is the gate which have, this is the only gate which have single input, okay. So it is the only gate with one input, whereas the other gate, whichever gate you consider, it will have at least 2 inputs. So a complement gate is this one, okay. So this is what it is. So you will see this particular waveform is just complement of A. So that is what is drawn here. So this is what a simple like timing diagram for any gate. But considering this logic, if you understood this logic well, if you understand this logic well, then you can use the same logic to show the timing diagram of any waveform, okay, of any output. So it is whether it is a counter or any function. If you have to show the output in the timing diagram waveform and the timing waveform diagram, then you can show that as well. And this is useful in your competitive exams as well, because in the competitive exams sometimes rather than giving the combinations of the truth table, they show it with the help of timing diagram. So we should able to understand this as well, okay. Okay, moving on to the next slide. Okay, moving on to the next slide. Okay, so you see, now though I have already told you the NAND gate, but that NAND gate is an universal gate, but we will, in this slide, we will try to understand that with the help of, because as we are telling that it is a universal gate, then we should understand, we should be able to implement all the basic gates at least, okay, with the help of this NAND gate and the NOR gate, because these two are the universal gates. So we'll try to understand, because you see, any function if you will implement, it will be nothing but the combinations of this basic gates. That is why they are called basic. Now if you can implement these basic gates with the help of any gate, okay, then that gate can be used to implement any bigger circuit, okay, any complex circuit as well. So we'll try to understand, we'll try to implement this gates with the help of NAND, and then later in the next slide we will implement all these basic gates with the help of NOR gates. So to implement this NAND gate, okay, with the help, to implement the NOT gate with the help of NAND gate, what we have to do, we have to combine both the inputs, okay. So you see, we have combined both the inputs. Now if you remember the operation of the NAND gate, then you see what will happen. here we will get A and here also A, okay, and the output will be A dot A whole bar. So this is what I am showing you, A dot A bar whole bar. Now A dot A, from your basic Boolean identities, if you remember, or if you just consider like 1.1, because these inputs will be what, 1 or 0 in digital. So if they are 0 0, then the multiplication will be 0. If it is 0 1, then it will be, I mean, if it is A's can be 0 because both the inputs are connected. So it is like single input gate. It became like a single input gate. Okay. So now if it becomes like a single input gate, then the input can be 0 or 1. So if your input is 0, then output will be 1. Okay, from your this particular functionality of the NAND gate. Okay, so this is why, I mean, if the input is 0, then the output will be 1. If input is 1, output will be 0. So that is why it is called a NOT gate. Okay, and this is equivalent to this. Then how to implement an AND gate with the help of NAND gates? So we have already seen that NAND gate is nothing but it is AND gate and a bubble at the output. So what we do, rather than using a bubble is nothing but an inverter or the NOT gate. So we use a NAND gate and then a inverter. So this is an inverter, so we used an inverter here. Excuse me. So now we'll see the OR gate. So how to implement an OR gate? So to implement an OR gate, what we do is we use again the De Morgan's law. So De Morgan's law, so the De Morgan's law, what we do is, by the De Morgan's law, we know that if we invert the inputs of the NAND gate, okay, so if we say, if our NAND gate is this, A dot B, and if we make the inputs complemented, so A bar and B bar, so complement is nothing but an, if let's say this is A and you want the complement, so you have to use a NOT gate here. So we have used a NOT gate. So NOT gate with the help of NAND gate only. So this is what we are using, a NOT gate, and then here we are getting A complement. So A complement and A complement is NANDed with B complement. So if you do this, then we get what? Help of De Morgan's, you can see that the output will be A plus B whole bar. The output will be rather this, A bar dot B bar whole bar. And if you solve this with the help of De Morgan's, so you will see that it is nothing but A plus B. So this is equivalent to your OR gate. So this is what your OR gate is. This is the output for OR gate. So that is why you say that this particular combination, the two NAND gates at the input and the two NOT gates, the two NAND gates at the input of an NAND gate itself, okay, will give you this OR gate. So try to remember these three circuits, because if you remember these things, these three circuits, what is equivalent for a NOT gate, what is equivalent for an AND gate, and what is equivalent for an OR gate for a non-NAND gate. Okay, in case of NAND gate, how to implement a NOT gate, AND gate, and OR gate. If you remember this, things will be very easy for you to convert a given AOI circuit and or in NOT circuit, that is the circuit which is implemented with the help of basic gates and OR and NOT. So this type of circuits are usually called AOI, okay, AOI circuits, okay. So this circuits you can implement with the help of NAND gates or the NOR gates if you remember this thing, okay. Okay, so we have seen the implementation of any function with the help of NAND gates in the last slide. In this slide, we will see the same for the NOR gates. So to implement a NOR gate, to implement a NOT gate with the help of NOR gates, again what we do is we connect both the inputs. So we have connected both the inputs of a NOR gate here. See the functionality, it is A plus A whole bar, and if you see, it becomes A bar, okay. Then to implement an AND gate, okay, OR gate, let's first try to understand the OR gate, that is more easier, okay. So OR gate is a NOR gate and at the output you use a NOT gate, so this, so then it becomes an OR gate, okay, same. Earlier it was for AND gate because we have used a NAND gate, here we are using NOR gate, so NOR gate is nothing but the complement of OR gate, okay. So the output should be complemented to get the complement again, because from our Boolean expression, Boolean identities, we know that double complement is equal to the same, okay. Double complement of a variable is equal to the variable itself. Now come to this AND gate. So to implement an AND gate with the help of NOR gates, what we do is again use the De Morgans. So the inputs are complemented. So complemented inputs, if NORed together, then we get an AND gate. Okay. So to complement each of the inputs, we use a NOT gate. So we have used NOT gates, and that NOT gate is implemented with the help of NOR gate. So to implement a NOT gate with the help of NOR gate, we have to connect these two inputs. So though we are using here a NOT gate, but it is with the help of NOR gates. Okay, NOR gates. So this is what it is, and then you have implemented an AND gate here. If you solve this, De Morgans, apply De Morgans, it is equivalent to this. So this was about your gates and how to implement any basic gate with the help of NOT gate. So in this slide, this is the quiz for this lecture. So try to solve this. What will be the function for this? Okay. So if this is A and this is B, so you just pause the video and then have to solve this. Okay, and tell me the answer. So if you are able to find the answer, then it is well and good. If you are not, then you can ask me it in the doubt class. Okay, we'll clarify it there. So this is what the question is, A and B, and you have bars here and the bar here as well. So you have bars at the input and at the output. So I want, if these two are the inputs, then what will be the output? Using your previous knowledge, whatever we have studied so far, try to solve this. Okay, what is this for function? This is question number 1, this is question number 2. So now, as we have seen all the type of gates there, then this particular gates are also used in your lab experiments. Okay, though you are doing all the experiments presently in the simulation lab, okay, online, but if you do the experiments in the laboratory, in the physical laboratory, if you are physically present here in the institute and you have to do the experiments, then what we do is we don't give you the single gates, but we give you some ICs. Okay, so those ICs are basically known by their numbers. Okay, and inside those ICs, what is there? So if you want a 2 input NAND gate, then the IC which you require is 7400. Okay, and this IC, how to identify its lags and all those things, that we teach in our physical laboratory, but you can use this notch. Okay, this is notch which you can see. If you keep it towards yourself, then you can see that from the if you keep it towards you, then the other side is 1. Okay, right side if you will see, this will be 1, 2, 3. This is how you can see. Okay, so the 1 will be, whichever lag is coming on the first, on your right side, that lag will be your first lag. So this is how you do. So 1, 2, 3, 4, 5, 6, 7, then 8, 9, 10, 16. Okay, up to 6, this 12, 13, 14. So this is 1 to 7 and this 8 to 14. So 7400 is in 14 pin IC. Okay, and which have like 4 2 input NAND gates. So this is what you have to remember. Okay, similarly 7402 is a 2 input NOR gate IC. Okay, so there are 4 2 input NOR gates. Then there is a 7404 IC. So 7404 is nothing but NOT gates. Okay, so NOT gates are there. So there are number of NOT gates here. Similarly 7408. So 7408 is 2 input AND gate IC. Then 7410. So it is 3 input IC, 3 input NAND gates. Okay, so similarly there are other. So you can use these ICs. So these are the ICs for your NAND and NOR circuits. Okay, then later on, let's see. Now in this slide, okay, so I stopped this particular part here. We'll start the next part from this next slide. Okay, thank you for listening.